Welcome back to this channel for practice problems for actuarial exams. My name is Krzysztof Ostaszewski. You can find information about me at smarturl.it/Jedi. My advice on how to pass actuarial exams is at smarturl.it/pass. This video channel is at smarturl.it/pass actuarial exams. Here's information about online seminars and study manuals for exams PFM, IFM, and LTAM that I offer. I direct the Actuarial program at Illinois State University. You can find information about it at smarturl.it/actuary. If you would like to offer a tax-deductible donation to support our students, please go to smarturl.it/help-ISU-actuary. Here's a problem for today for exam LTAM, long-term actuarial models. It's problem number 3 from last exam LTAM in fall 2019 in written answer section. An insurer uses the following model for joint life policies. As you can see, there are 5 states. It's a multi-state model. State 0 is when both X and Y are alive. State 4 is when both X and Y are dead. State 1 is when X is alive, Y is dead. State 2 is when X is dead and Y is alive. And State 3 is when X is dead and Y is dead. And so you may wonder, how is State 3 different from State 4? And it is different this way, that to get to State 4, X and Y have to die simultaneously, while State 3 is the state of both of them being dead, but one of them died first and then the second one. Of course, we can see that states 3 and 4 are absorbing, and of course you can see that there is no going back to State 0 from State 1 or State 2. You are given the following additional information. Mu W star is the force of mortality for a life age W under the standard ultimate life table. Now this W should be in italics. Mu X plus T colon Y plus T 01 is mu Y plus T star, so the one from standard ultimate life table for age Y plus T, minus 0.005. Mu X plus T colon Y plus T 02 is mu X plus T star, so the one from the standard ultimate life table for Hx plus T, minus 0.005. And mu X plus T colon Y plus T 04, so the force of transition to death of both of them that happens simultaneously, is 0.005. Mu X plus T colon Y plus T 13, so force of transition from State 1 to State 3, is 1.2 times mu X plus T star, so that's the force of mortality for life age X plus T in the standard ultimate life table multiplied by 1.2. And mu X plus T colon Y plus T 23 is 1.05 times the force of mortality at HY plus T from the standard ultimate life table. The interest rate is 5%, and that's of course the interest rate in the standard ultimate life table. For X equal to 40 and Y equal to 50, A bar X colon Y colon angle 10 0 0, so annuity paid starting in State 0 and paid while in State 0 is present value is actuarial present value is 7.8487, and A bar X colon Y colon angle 10 03 is 0.00789. Describe question A. Describe 2 ways that dependency is incorporated in this model. B. Calculate 10p 50 23. So that's corresponding a transition from State 2 to State 3, starting at age 50, within 10 years. Calculate 10p x colon y 00 for x equal to 40 and y equal to 50. That's the probability of remaining in state 0 for 10 years. And we don't have to worry about going out of it and coming back because there is no going back once you leave state 0. So this is continuous state, but it's just probability of staying in state 0. C, a couple, X who is age 40 and Y who is age 50, buys a special 10-year joint life insurance policy with the following features. Level premiums are payable continuously while in state 0. A death benefit of $100,000 is payable immediately on the second death. If the deaths are simultaneous, the death benefit is increased to $300,000. Calculate the annual net premium rate. Part D. State with reasons whether each of the following would be higher, lower, or stay the same if mu x plus t colon y plus t 23 is increased to 1.15 mu y plus t star, so 1.15 times the force of mortality at age y plus t from the standard ultimate life table, assuming all other transition intensities are as given above. And you have a bar x colon y colon angle 10 0 0, big A bar x colon y colon angle 10 0 3, A bar x vertical line y, and we'll explain later what this means in just a moment. The annual net premium for the contract in C. This number 3 is reversionary annuity. It's a topic that you should know from whatever source of study you use. And of course it's described in my study manual. For part A, here's a solution I should say. For part A, 2 ways that dependency is incorporated in this model. Because there is this possibility of both of them dying simultaneously, that kind of a model or that kind of situation is called common shock. And simultaneous deaths indicated by transition from state 0 to state 4. And there is something that is commonly called broken heart syndrome. Mortality of surviving life is higher than individual mortality when both are alive. So in this model, we have mu 13 is greater than mu 02, and mu 23 is greater than mu 01. In other words, once one of them dies, the probability that the other one die is higher because of the force of mortality corresponding to the other one dying is higher. For part B, part 1, we have we need to calculate 10p50 3, so transition from state 2 to state 3. And that's 1 minus e to the minus integral from 0 to 10 of 1.05 mu 50 plus t star dt. And that's corresponding to the way this force of mortality 2, 3 works. It is equal to this expression that we have here, and probability of surviving from it is e to the minus the integral of the force, but we are asking for the probability of transitioning from 2 to 3, so in a sense probability of death from that force. And that's why this is 1 minus e to the minus the integral. So that's equal to 1 minus e to the minus the integral from 0 to 10 of mu 50 plus t star dt to the power 1.05. And the reason why we separate this is because once it's written this way, we know that mu star is the force of mortality corresponding to the standard ultimate life table. And of course, e to the minus the integral of the force of mortality in this table is simply the probability of survival over 10 years for a 50-year-old based on the standard ultimate life table. So that probability to the power 1.05. So we have 1 minus that probability to the power 1.05, and we can find that probability just by taking the ratio of the population size at age 60 divided by population size at age 50 from the standard ultimate life table. And once we plug those in and calculate this, this is approximately 0.0206784. Next, we look at 10p 40:50 00. So the probability of the joint life status 40:50 remaining in state 0, which is both of them are alive, over 10 years. And that's equal to e to the minus the integral from 0 to 10 of the sum of all the forces that would take this joint life status out of state 0, which is mu 01, mu 02, and mu 04, because from state 0 you can go to states 1, 2, and 4 if you leave state 0. And then we plug in what these are in terms of the forces related to the standard ultimate life table. And what do we get? Well, we get mu 50 plus t star minus 0.0005 plus mu 40 plus t star minus 0.0005 plus 0.0005. Okay, that 0.0005 that remains, it's negative, it's going to be minus that, but there's a minus sign in front of the integral. And if we just take this to be, well, it's right now integral from 0 to 10 of sum of certain expressions. So the integral of a sum is a sum of integrals, and then e to the sum is e to the first thing times e to the second, and so on. So if we take just the portion with 0.0005, it's going to, what will stay there is e to the minus integral from 0 to 10 of negative 0.0005 dt. So minus minus cancels, and of course it's a constant, so this becomes just e to the 0.0005 times 10. If we take the integral of the 40-year-old force, that's just the probability of survival over 10 years based on the standard ultimate life table. If we do the same for the 50-year-old, that's the 10-year survival probability based on standard ultimate life table. But, well, once you go from 40, 10 years forward, you're 50, and when you go from 50 to 10 years forward, you're 60. So this product of those two probabilities is simply the probability of going from age 40 to 60, based on the standard ultimate life table. And unfortunately, this baby here is missing a 0, so let's fix that. Yes, because this remains the same. Oh, no, it's not missing a 0. It's my fault. It's multiplied by 10, so it's correct. My apologies. So this is e to the 0.005, and this is the population size from standard ultimate life table at age 60 divided by population size from standard ultimate life table at age 40. And we plug those in, calculate it, and we get approximately 0.9776539. For part C, we are given that A bar 40:50: angle 10:00 is 7.8487, and big A bar 40:50: angle 10:03 is 0.00789. So we use the equivalence principle and take the actuarial present value of the premiums equal to the actuarial present value of the benefits. And we get what you see here. And the premium annuity is the one that is given, luckily. And then the big A bar 03, actuarial present value benefit at 100,000, that's also given. So the only thing is that benefit in the case of simultaneous death, 300,000. And of course, we're using this equivalence principle here to derive the premium. So we need to calculate A bar 40 colon 50 colon angle 10 04. And that's the integral from 0 to 10 of e to the minus delta t. That's just the present value factor to calculate the present value of the benefit, which for the unit policy is just 1, so this is the present value of 1, times TP 40 colon 50 00. Now notice that angle 10 is already represented in the integral from being from 0 to 10, so this is the probability of survival up to time t of the joint life status 40-50, and then instantaneously being whacked by force taking them from state 0 to state 4, so that they die simultaneously. That's mu 04 that you see there, dt. Okay, and that mu 04 is a constant, so we put that constant in front. That's 0.0005 times the integral from 0 to 10 e to the minus delta t times TP 40 colon 50 00 dt. Well, this expression is actually just A bar 40 colon 50 colon angle 10 00, which is given. So we plug that in, and we get 0.00392435. So now we can calculate the premium. And the premium is 100,000 times the actual present value of a unit benefit for transition from state 0 to state 3, plus 300,000 times the same for transition from state 0 to state 4, divided by the annuity, which describes how the premium is paid. All of these are now given. We plug them in, and we calculate it, and we get approximately 250.5262. And here is part D. We are determining whether each of the following would be higher, lower, or stay the same if mu x plus t colon y plus t 23 is increased to 1.15 mu y plus t star, assuming all other transition intensities are as given above. Well, a bar x colon y colon angle 10 00, this quantity stays the same because transition intensities for leaving state 0 do not change, and it is not possible to return to state 0 after leaving it. So the transition from state 2 to state 3 is interesting, but it does not affect the way this annuity is paid. A bar x colon y colon angle 10 03, well, this quantity would be higher. If y dies first, there is no impact. But if x dies first, y is likely to die sooner because of this property of the model of the broken heart syndrome, and this increases the expected present value, actual present value of this life insurance. A bar x vertical line y, in the model in this problem, this quantity is denoted by A bar x colon y 02. This quantity would be lower. This annuity is payable while y is alive after the death of x. And it's called a reversionary annuity. And it starts paying once one of them dies to the other one, as long as the other one lives beyond the first death. And again, it's called a reversionary annuity. Since after the death of x, y is likely to die sooner, the expected present value, or actual present value, will decrease. In part 4, the annual net premium for the contract in C would be higher. The values of A bar 40 colon 50 colon angle 10 00 and big A bar 40 colon 50 colon angle 10 04 would stay the same, but big A bar 40 colon 50 colon angle 10 03 would increase, so that the premium for the contract in C would decrease. I apologize, this is another typo. This is, of course, increase. The cost of benefits would increase, the way the annuity is paid would be the same, so of course the premium would increase. And I say it here, I don't know why I put the wrong word here, but yes, the premium for the contract in C would increase. Please remember this is copyrighted material. The problem itself belongs to the Society of Actuaries. The solution is mine. Good luck in your studies and good luck on the test.